Hi guys, in the last lecture we studied about the no load test that was used to determine the equivalent circuit parameters of the induction motor. From this test we determined the rotational loss and no load stator copper loss. Okay, we also determined the resistance, that is R1, stator resistance, stator reactance and magnetizing reactance. Then we studied about blocked rotor test, in which the rotor was not rotating, hence NR was 0 and slip was 1. This was used to determine the blocked rotor resistance, blocked rotor reactance and blocked rotor impedance. We studied about the stability of induction motor, and there we studied the condition that dTL by dN should be greater than dTE by dN. This was the condition for the stability of the induction motor operation. In this lecture, we will study about the induction motor starting, that is how to start the induction motor so as to reduce the starting current. So in case of induction motor or in case of any other motor for that purpose, starting current is high. So while starting any motor, the aim is to increase the starting torque but to reduce the starting current. Why to reduce starting current? Because since starting current is high, it may damage the machine. So it can cause damage to my machine. That is why we need to reduce the starting current. But if we reduce the starting current, then by default the starting torque also reduces. So that is the disadvantage, that if we want to control the starting current, I will lose in terms of starting torque. So if starting torque reduces, starting current reduces, starting torque also reduces. So there are primarily two methods of starting of induction motor. One is the direct online starting, it is also called as DOL, in which we apply the full supply voltage across the stator terminals to start the induction motor. Other is called as reduced voltage starting, in which we do not apply the rated voltage but rather a lesser voltage to start the induction motor. So reduced voltage causes reduction in starting current, but it also causes reduction in starting torque. So here we can control the starting current, but as well as the starting torque will be reduced, which can cause inoperation of the machine, because as I told you in the last lecture, if the starting torque is less than load torque, the machine will fail to start. That is why we cannot have the starting torque reduced too much, because otherwise the motor may not start. So let us see each and every method. So first is the direct online starting. At starting, slip will be 1, that is NR will be 0. So what will happen to the rotor circuit? In rotor, this will happen X2 R2, because R2 by S will be equal to R2. So this impedance Z, which is under root R2 square plus X2 square, is called as ZSC, that is the short circuit impedance. Why I am calling it as short circuit? Because the mechanical power resistance, that is R2 1 minus S by S, becomes 0. So this resistance gets short circuited, hence it is called as short circuit impedance. So it is the impedance of the rotor circuit at standstill. Okay, so ZSC is the rotor impedance at standstill. Standstill means when motor is not rotating. So the impedance offered by the rotor circuit is ZSC. Okay, so this will be constant under root R2 square plus X2 square. Now, when we are talking about the starting, what will be the rotor current? Rotor current will be V1 by ZSC. Okay, because the impedance of the rotor circuit is ZSC, so it will be V1 by ZSC. So this is your starting current at the rotor side. the relation between primary and the stator and the rotor current will be I1 by I2 is equal to N2 dash by N1 dash. So I can call I1 will be equal to I2 into N2 dash by N1 dash. This is the current on the primary. So I starting will be I2 starting into N2 dash by N1 dash. Okay. When we are talking about the torque, what is the expression for torque? The torque is given by 3 by omega s into I2 square R2 by S. So starting torque will be 3 by omega s I2 starting square R2 because slip will be 1. Full load torque will be 3 by omega s I2 full load square into R2 by full load slip. So if I take the ratio starting torque by full load torque, it will be I2 starting by I2 full load square into S full load. Now these are the currents on the rotor side, but I can measure the current only on the stator side because stator side electrical terminals are present. So what to do is, we will transform using the relation I2 will be equal to I1 into N1 dash by N2 dash. So this factor of N1 dash by N2 dash will get cancelled out between I2 starting and I2 full load. So starting torque by full load torque will be I1 starting by I1 full load square S full load. It is also written something like this: I starting by I full load square into S full load. So that is the relation between starting torque and the full load torque. And this I starting can be written as ISC because at starting the impedance is called as short circuit impedance. So current will be short circuit current. Here ISC means V1 by ZSC. ZSC is the rotor impedance at the time of starting. Here the mechanical resistance is short circuited and hence it is called as short circuit impedance. So that is your direct online starting. Now we will move on to the reduced voltage starting and we will compare the starting torque produced in case of direct online as compared to the reduced voltage. So first method is stator reactance starting. So here what I am doing is I am using a potential divider. So the line voltage is root 31 V1, but by using potential divider I am making it root 3 x V1 where x will be less than 1. So I am reducing the voltage. If I reduce the voltage, starting current which is now x V1 by ZSC, it becomes x times I short circuit. So starting torque which is proportional to I starting square now becomes x square ISC square. That means the starting torque is now becoming x square times the initial value. So now if we take the ratio of starting torque to the full load torque, what was the ratio? T starting by T full load, I starting by I full load square S full load. I starting can be written as ISC by I full load square S full load. Okay. So that means the starting torque becomes x square times as compared to the direct online starting. So suppose if x is half, then the torque will become 1/4. So here we have reduced the starting current, but the torque also has reduced significantly. Okay. So when we were applying a voltage V1, torque will be, let us say, T1. When we apply x V1, it will become x square T1. Okay. So that means torque with direct online upon torque with reactance is 1 by x square. So direct online starting has the maximum torque, but the disadvantage is that the rotor current is high, which can damage the rotor windings. Okay, this effect is very less in the your squirrel cage induction motor. Why? Because squirrel cage induction motor has a rigid rotor. The rotor cannot get damaged easily, but in wound rotor, the rotor windings can get damaged with a high current flow. The other method to reduce the voltage is the auto transformer. Here I am using the transformation ratio 1:x. So if V1 is the input voltage, it will be transformed into XV1. So that will cause starting current to be XV1 by ZSC, which is X into ISC. Okay. So here the current that will be flowing will be X into ISC, due to which the starting torque is proportional to I starting square. It becomes X square times ISC square. So starting torque becomes X square times short circuit torque, or we can say X square times torque under direct online starting. Okay, but the thing is, here the stator current, if we find out, we know the MVA on both the sides must be same on the transformer. So primary voltage is V1, current is I1. Secondary voltage is XV1, current is X into ISC. So I1 will be X square ISC. Here the advantage with the auto transformer starting is current is reduced by X square times the current drawn from the stator winding or drawn from the supply is becoming X square. In the previous method the current was becoming X times, but here it is becoming X square times. Here X is less than 1. That is, if suppose X is 0.5, then starting torque becomes 0.25 times, that is 25%. But here starting current also becomes 25%, which is 0.25 times I direct online starting. Okay. So that way, here one advantage is that for the same reduction in the starting torque, we are getting more reduction in the current drawn from the supply. That is a big advantage in case of auto transformer starting. Okay, that the current drawn from the supply is reduced by X square times. The next method to reduce the voltage is star delta starter. Usually, the stator winding of the induction motor is connected in delta. So it is only used where the stator winding is in delta. At starting, what I will do is I will connect it in star. That is only at the time of starting. So that when the motor is running, I will again convert it to delta. So if I convert it to star, that means earlier the voltage was V1. So the short circuit current or the starting current was V1 by ZSC. Now I have converted the voltage per phase to V1 by root 3. So starting current will become V1 by root 3 ZSC. Now we know starting torque is proportional to I starting square. 1 by 3 V1 square by Z square SC. So that means 1 by 3 the starting torque in case of delta. TSTD means the starting torque with a delta connection. So the starting torque with the star delta starter becomes 1/3 of the starting torque that would be with the delta connection. Okay. So here, if the phase current is I1, I1 is actually ISC, the line current in delta will be root 3 times ISC. This is for delta. In case of star, voltage becomes V1 by root 3. So I starting becomes 1 by root 3 ISC, that is for star. Okay, but in case of star, the line current is same as phase current. So what will happen is if we take the ratio of line current to the in star connection to the line current in delta connection, that is IL star upon IL delta. IL star is how much? 1 by root 3 ISC. Delta is how much? Root 3 ISC. So that is 1 by 3. So the line current also becomes 1/3 as well as the torque becomes 1/3. Okay, so that is the advantage with the star delta starter, that the starting torque is reduced by 1/3 times. That is a disadvantage, but the starting current also reduced by 1 by 3 times of the original value. Here I am comparing the line currents in star connection to the line currents in delta. So what we do is, initially we will connect the windings in star connection, and as soon as the motor is under running condition, we will convert back to the delta. This method can only be applied to motors which have delta connected stator winding. Because the winding is already connected in star, then I do not get any advantage, because winding is already in star. How do I convert it to star? It is already in star. So but if it is in delta, I will convert it to star and reduce the voltage to reduce the starting current. Okay. Now what is the difficulty in case of star delta starter? First of all, when you are changing from star to delta, you have to take care that the speed is around 80% rated speed. Otherwise there are very high currents. Why there are high currents? Whenever we have to convert from star to delta, we will have to disconnect the winding, because we are changing the connection. If we disconnect the stator winding, that means stator current is reduced to 0. But the flux cannot be instantaneously reduced to 0 due to magnetic inertia. So what happens? The flux remains constant. That is, the rotating magnetic field is still present. This rotating magnetic field will cut the stator conductor. And when it cuts the stator conductors, it will induce some EMF in them. Okay. Now what happens when we connect the winding in delta? We will apply the supply voltage, that is V1, but here there is some EMF E. Suppose this V1, that is the applied voltage, and E, that is the induced EMF after disconnecting the winding, both are in phase. Total voltage becomes V1 plus E. That is a very high voltage which can cause current to be high in the stator winding, that is 10 to 15 times full load current, and it can damage the stator winding. Okay, so that is the difficulty in the star delta starter. That is, when we will switch from star to delta, EMF will be induced in stator winding, and if it is in same phase with the stator applied voltage, high currents will be circulated in the stator winding. So I have to devise some method in which I do not have to disconnect the winding while going from star to delta. If I do not disconnect the winding, then there is no EMF induced and there are no high currents induced in the stator winding. How to do that? Like this, the windings are in star initially. Here there are 3 resistances which are disconnected right now. So what I will do is I will connect them. Okay, I am moving from star to delta. First I will connect these resistances. Then I will remove this short circuiting here. This has been removed here. Now what to do is, now short circuit these resistances. Now if you see, this connection is actually delta connection. Between these two terminals there is one winding. Between these two terminals there is one winding. Between these two terminals there is one winding. So it has become the delta connection. That way I never had to disconnect the windings from the supply, and as well as I have changed the connection from star to delta. So it is a modified star delta starter, which removes the difficulty that we have to disconnect the winding from the supply. Okay, so that is one of the methods for starting the induction motor. So let us summarize what we have learnt in this lecture. We first saw direct online starting. Here we saw starting torque by full load torque is I short circuit by I full load square S full load. Then we saw stator reactance. Here it was X square times ISC by I full load square S full load. But here starting current becomes X times ISC. Then we saw auto transformer. Starting torque by full load torque is X square ISC by I full load square S full load. Here starting current became X square times the I direct online starting. And the last we saw star delta starter. Here starting torque by full load torque became 1 by 3 ISC by I full load square S full load, and here I star by I delta became 1 by 3. So this is the method for starting the induction motor. So starting of induction motor is an important concept as per the gate perspective. So try to remember these formulas, at least the ratio of starting torque to the full load torque for different starting methods. In the next lecture, we will see how to control the speed of induction motor so as to obtain a variable speed drive.